So the next in line is Pietro Ferrero from Oxford University that will talk about M2 and D3 branes wrapped on spindles. Thank you very much.
Thank you. So today we'll discuss some work done in collaboration with Jerome Gauntlet, Juan Manuel Perez-Pina, Dario Martelli, and James Parks on the idea of wrapping M2 and D3 branes on spindles. To begin with, let me give you a brief introduction about the topic and the general context. Standard holography dictates that d plus one-dimensional branes at Calabi-Yau singularities are dual to d plus two-dimensional CFTs or SCFTs. And following this seminal paper by Maldacena and Nunez, we can put these field theories on a space which looks like RD times a compact two-dimensional space sigma. And if we follow the RG flow to the infrared, we effectively compactify this theory, and we get a CFT or an SCFT on d dimensions. And the dual description of this in supergravity is a d-1 black brane solution, which interpolates between ADS-D plus 3 space at the boundary and an horizon which looks like ADS-D plus 1 times sigma. And the idea is that then we realize a duality between this horizon and the compactified theory in the dimensions. So we will consider this scenario in the specific case of ADS4 black holes and ADS5 black strings. And in these two cases, there's been quite some progress recently on the counting of microstates for black holes and black strings. In the case of ADS4, we have a UV which looks like, which is dual to a 3D n equals 2 SCFT arising from M2 branes. And the horizon of these black holes looks like ADS2 times sigma, which is dual to a one-dimensional superconformal quantum mechanics. And in this case, the counting of microstates is typically done using I extremization. On the other hand, we have ADS5 black strings. In the UV, they are dual to 4D n equals 1 SCFTs arising from D3 branes. They have an horizon which looks like ADS3 times sigma, which is dual to two-dimensional SCFTs. And here the counting can be done using C extremization. So we will consider precisely these two pictures, but let me start with the case of ADS4 black holes. And in particular, I will consider black holes in the Plebanski-Demianski class. So Plebanski-Demianski black holes are solutions to Einstein-Maxwell theory. They're known from the 70s. And here we consider the case with no nut parameter. The solution is then described with 5 parameters. You can see here it looks more or less like a Kerr-Newman black hole. And we're considering a negative cosmological constant to get asymptotical ADS. And the most important feature is that we consider accelerating black holes. And this reflects in the presence of this overall warping function. And this has been considered already in various works, but I will present some features that are related to acceleration, which are somehow new in the fact about accelerating black holes is that they have conical singularities at the poles of the horizon, which in these coordinates corresponds to theta equals 0 and pi. And so one can wonder whether we should just throw away these solutions. But since, of course, the answer that we provide is no. We can rather uplift these solutions to 11 dimensions, constrain suitably the parameters of the black hole, and regularize the solution in 11 dimensions. Let me mention that this is just one possible option, but many others have been considered in the past. Sorry, can you still hear me?
Yes.
Okay, thanks. So let me explain briefly how this idea of uplifting and regularizing works. For the uplift, I will consider this ansatz, which comes from a paper from Gauntlet and Varela from 2007. The metric in 11 dimensions is simply given by here the 4-dimensional metric, and then we uplift on a Sasaki-Einstein manifold, a Sasaki-Einstein 7 manifold of the regular class. And this can be written in itself as a fibration, U1 fibration, over a Kähler-Einstein manifold of positive curvature. This ansatz solves the equations of motion of 11-dimensional supergravity and preserves supersymmetry. So by this uplift, we obtain a local solution in 11 dimensions, which, however, is still singular. So what we want to do is check global regularity. This goes into a 2-step procedure. The first step is to analyze the space in the theta and phi directions, which are essentially the directions along the horizon of our black hole. And near the poles, theta equals 0 and pi, as I anticipated, we have conical singularities. Indeed, the metric here, you can see it looks like R2, where p plus minus is the metric function p evaluated at the poles. And due to the acceleration, p minus is different from p plus. So we cannot make this regular by a suitable choice of the periodicity of phi. So we have to live with these conical deficits, but rather than keeping them arbitrary, we can quantize them and make the space into a weighted projective space labeled by 2 integers, which we call the spindle. The way we can do this is constrain the parameters which enter in p plus and p minus in such a way that p plus over p minus is simply a rational number. This spindle or weighted projective space can be embedded in R3. It looks more or less like this for some values of n plus minus. And if you're wondering why we call it a spindle, you can think of the Sleeping Beauty, where this is a spindle. The second step of the procedure is to consider the theta, phi, and psi directions, where psi, I remind you, is the direction of vibration of the Sasaki-Einstein over the Kähler-Einstein manifold. And we can make the space in these 3 directions into a length space S3 mod ZQ. And this is achieved by a further constraint on the parameters, namely that mass is related to the ratio between magnetic charge and acceleration. And importantly, let me stress that this constraint is compatible with supersymmetry. The result is that if we fix the non-compact directions, so time and the radial direction, we obtain a Riemannian manifold Y9, which is a completely smooth length space vibration over the Kähler-Einstein 6. So we start from a singular ADS4 black hole, we uplift it, and we make it regular by constraining the parameters. Let me then look at the horizon of this black hole. In the supersymmetric and extremal case, the metric is the following, and importantly, it has an ADS2 factor, and here we can see these 2 directions, y and z, which parameterize a spindle. The metric depends on 2 parameters, sorry. The first, j, which appears here, is continuous and is related to rotation, while the second, which is hidden in the functions q and h, is fixed, as you can see here, by n plus minus and j, and is related to acceleration. This solution still has electric charge, magnetic charge, and angular momentum, which is related to electric charge by the BPS equations. What I want to discuss of this solution is essentially 3 aspects, which also allow me to give you a bit of outlook. The first is the entropy. In the supersymmetric and extremal case, 2 possible expressions. The first one is the ratio between angular momentum and electric charge, and the second is in terms of electric and magnetic charge and the Euler number of our spindle. And importantly, these 2 formulas are related to other formulas present in the literature for ADS4 non-accelerating black holes. An important question is, of course, whether we can reproduce this entropy from a field theory computation, which we haven't done in the ADS4 black holes case, but we have done it for the 3 branes, and in particular for the ADS3 cross-spindle solutions that I will briefly mention at the end. The second aspect is that of supersymmetry, which in the presence of a magnetic flux is typically realized with a topological twist, which means essentially identifying the spin connection and the gauge field. And to see if this is the case here, we should compare the Euler number of the spindle with the magnetic flux across the spindle. And what we find is that the 2 are not proportional, so supersymmetry is not realized with a topological twist, which raises the question, which is still standing, of how supersymmetry is realized in the dual field theory. The last aspect that I would like to discuss is that of the R-symmetry of the 1D theory that we obtain as dual of the horizon. And studying the spinor bilinears of our ADS2 solutions, we find that the R-symmetry of this 1D theory is given by a mixture of the R-symmetry of the 3D parent theory and the U1 isometry of the spindle. And this persists even in the case in which we set this parameter j, which is related to rotation, to 0. And this is, as far as we know, the first example of mixing between higher and lower dimensional symmetries in a supergravity solution, even in the absence of rotations. To conclude, let me just briefly mention what happens for the case of D3 branes wrapped on spindles. In this case, the picture is in type 2b, supergravity, and it regards ADS3 times spindle solutions of 5D minimal gauge supergravity, which can be uplifted to 10 dimensions by regularizing the conical deficits of the spindle. And what we obtain is regular ADS3 times Y7 solutions of type 2b, which are just a reinterpretation of solutions that were already found in 2006. There are some analogies between the D3 branes and the M2 branes case, or ADS3 versus ADS2. The first is that we still have an interpretation for our supergravity solutions as branes wrapped on spindles. Even in this case, we don't have a topological twist, and we still have a mixing between higher and lower dimensional symmetries and the isometries of the spindle. The main differences, and then I will conclude, are that we don't have the full geometry in the type 2b case. In particular, we can only conjecture that our ADS3 solutions arise as near horizon geometries of 5D black strings, but we don't know the full solution. The second difference is that to preserve the isometries of ADS3, it's not possible to add a rotation parameter, so there is no continuous parameter in the solution. And finally, the entropy and the R-symmetry mixing have been reproduced using a field theory computation, in particular using the anomaly polynomial technique. And this confirms our ADS-CFT interpretation for our solutions. Thank you for the attention.
Okay, thank you very much for your nice talk. Are there any questions or comments?
Yes, I have a question.
Yes.
So I didn't understand what you mean by acceleration. So is this a rotational acceleration? And if so, is there an external force that makes this acceleration?
So the acceleration is along the z-axis. So if you take cos theta to be the angle from the z-axis, you have an acceleration in that direction, which is what creates the conical deficits. And the way that people treated this in the literature was typically to implement some external force, either inserting some string or some external magnetic field. Here, we didn't consider that approach. So we don't really have the interpretation of a force pushing the black hole. Rather, we consider a different way to regularize the solution.
Okay, but there must be some force that makes it accelerate, right?
That's provided by the...
Well, it's not... Sorry?
I think that's provided by the conical singularity.
Yeah, exactly.
So you have a string pulling it.
Yeah, exactly. It's only here we don't insert the external string or magnetic field in the solution. But yes, the conical singularities are what provides the force that makes the black hole accelerate.
Okay, thanks.
Do you have an acceleration horizon as well for this?
So yes, in general, yes. You can see here this polynomial Q, which is the radial function, as is degree 4. So it has 2 ordinary and 2 acceleration horizons. And in principle, we should worry about this. But in the supersymmetric and extremal case, there are only 2 real roots which correspond to ordinary horizons. So we don't have to worry about the acceleration horizons. If you set rotation to 0, there is a subtlety, an acceleration horizon does appear, but only in the limit when you have supersymmetric, extremal, and rotating.
Okay. Any other questions? Maybe you have time for a short one. If not, we can thank